Okay, so in this video we're going to go over how to properly write electronic configurations for atoms. In order to properly write, you need to know three different rules. I'm going to tell you right now, I'm not going to ask you to state any of those rules, but you will have to be applying those rules in order to do the correct electronic configuration. And again, once you get used to applying these rules, it becomes kind of natural. You don't really have to even think about them. You can just read it off a periodic table. But it's good to go over the rules to begin with. So the Aufbau principle is the most important rule. It basically states that the orbitals are filled in increasing order of energy. Now, there's two ways to find out how to calculate the energy of the orbital. So let's take like the order. So you have to add the n plus the L value. So a 1s, the n value is 1, s value is 0. This has an energy meter of like 1. Again, this 1 doesn't correspond to its actual energy level. It's a representative number that tells you relatively how much it has, let's say, compared to a 2s orbital, which has 2 plus 0 equals 2. So that is relatively higher energy. So 1s gets filled first, then the 2s gets filled. Then you fill a 2p because this is 2 plus 1 equals 3. Then you fill a 3s because that's 3 plus 0 equals 3. So you'll note that these two are the same, but if two have the same energy, the higher n has higher energy. So 3s has higher energy than 2p because it has a 3 instead of a 2. So you fill in the s orbital before you start filling in the 2s, before you start filling in 2p, before you start filling in 3s, right? Pauli's exclusion principle states that each orbital has 2 electrons, a maximum, and we talked about that, and both those electrons have to have opposite spin. So in each suborbital, so like a 2p suborbital, there will be 1 electron with upspin, 1 electron with downspin. We'll get to Hund's rule in a bit, but basically let's just focus on Aufbau. This is another shortcut to remember. If you write the electronic configuration like 1s, 2, 3, 4, 5, 6, 7, 2, 2p, 3d, 4f, and you draw arrows like this gives you the order in which these electrons are filled. So you start with 1s, then you fill 2s, then you fill 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5, etc. You fill these. You get the idea. You just follow the arrows. I don't particularly like this method because it involves carrying this little thing around with you all the time, which I don't really like. So there is an easier way to say which order these orbitals are being filled, so we're going to do it that way. Okay, this is a energy level diagram. We have to know how to draw these. And this, again, increasing energy corresponds. So the 1s has the lowest energy, then you kind of have the 2s, 2p with slightly higher energy, then 3s, then 3p with higher energy, 4s, 3d next, and then you fill a 4p, 5s, 4d, 5p. This gives the order, and you just stack them up looking like this. So all the s orbitals are here, p orbitals are here, d are here, f's are here, in proper order of energy. So we'll be drawing some energy level diagrams, and we have to know how to do that. And each of these, so you'll note here that look at this p orbital. I have 3 little boxes. So if I want to do boxes instead of circles, this is what a p orbital looks like, because you know that the p orbital has 3 different magnetic quantum numbers corresponding to -1, 0, and 1. And what Hund's rule states that is, let's say I start filling in my first electron here. The next electron will go into this and then this, and then only I start doubling up my electrons. I do not start filling in my electrons like 1, 2, 1, 2, 1, 2. Instead I go 1, 2, 3, 1, 2, 3. For a d orbital, say here, I go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, like that, instead of doubling up here, doubling up here. So I want each orbital to have at least 1 electron, and then I start doubling up. That's what Hund's rule says. And again, it's kind of complicated. At least if you're looking at this for the first time, to understand it without some examples. So that's exactly we're going to practice with. We're going to practice with some examples. Here also comes a description on how to look at it just by looking at a periodic table. For this, we will kind of have to, let's see if I can. Snip. I just need this bit so that I can write on it. Okay. Hopefully it was here. Yes. Interesting. I guess I'll have to open it with another app. Okay, I can write on this though, so that's the main idea. Okay, so we will have to first define our block elements. So here we have this block here is what is called the S block of elements. It is so called because the electron goes into the S orbital. Excuse me. Just give me 1 minute. All right. Before we get into the blocks, I think that's part of the next PowerPoint. So we'll just start writing electronic configurations here. But we'll learn how to do it looking at a periodic table. So for helium, you know that you start with the 1. So basically helium has 2 electrons. So you start with the 1s2. So that's the electronic configuration for helium. It's just 1s2 because the 2 electrons are going into the 1s orbital. So boron. Boron would be, so you'd write 1s2. So 1 electron here, 1 electron here. Then you start filling the 2s orbital. So you have 2s1, 2s2. And then you have the 2p orbital where you hit boron, and that would be 2p1 is the electronic configuration of boron. So how that would look in terms of a electronic diagram would be 1s2, 2s2, and then to the side we have, this is what a p orbital looks like, 2p1. This is the electronic configuration for boron. Now carbon has an electronic configuration of 2p2. So you have to be very careful. The second electron does not go into this second p orbital, it goes into here. Because of Hund's rule, right? So this is for carbon. If you wanted to do oxygen, I'd have to do 2p3 and 2p4 because that is the electronic configuration of oxygen. Again, we'll get to how to get which order to put these in a little bit. We're going to see that. Whoops, where did my things go? There. And neon would be 1s2, 2s2, 2p6. So you just read them off the periodic table. Like so. So you go 1s2. It's kind of, the 1s2 is hard because it's like all the way over here, but this is a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and we're getting into basically how to read this thing. So we'll look at the next PowerPoint if I can find it. This is S&P. We're getting to the S block and the other block of elements. So again, these are the S block elements. Why are they called the S block elements? Because if you write the electronic configuration of these elements in this block, the last electron will go in an s orbital. So that's why they're called the s block elements. If you put these over here are called the p block elements, except for helium, because helium is technically part of the s block because it's a 1s2. It's just put here because of its noble gas configuration, because it has very similar properties to all the other noble gases. Therefore, it's shifted over here on the periodic table, but it is part of technically an s block. Here, the p block, the last electron goes in a p orbital. Here's your d block, last electron goes in a d orbital. And this is your f block, last electron goes in an f orbital. And we kind of see that by the numbers. We know p blocks have 6 electrons, so this will be a p1, p2, p3, p4, p5, p6, right? We know D has 10. This will be D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. So as you put it, as each of these elements have one more electron than the previous one, so as you keep adding one more electron, they go into certain orbitals, right? And the position on the periodic table really tells you which orbitals they are going into. Same way F has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, because these two are technically part of the D block here. The element goes in the D block. But again, this is how you kind of figure it out. You just look at where it is, and then you read. So if you're looking for germanium, for example, you go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So we'll note that when you're reading these, this is basically when you're reading an s block or a p block, the number corresponds to exactly which period these are, right? So this is a 1s2. This will be a 5s2. This will be a 6s2, that kind of thing. I'm going to reopen because it's messy. There. That's better. For the D block, it's n-1d. What does that mean? So even though this is part of the 4 period, these are the 3D elements. Because the D block has a high energy, this is technically, you fill in the you fill in the 3D right after you fill in the 4s. And if you look at your energy diagrams, that's what you fill in next. So this is the 3D block. So it's n-1. So this is the 4D block, even though it's in a 5 period. This is the 6D block. 5D block, and this is the 6D block, even though they're in 6 and 7. Same way, the F block, starting from here, this is n-2 F block. So this cerium starts after the 6s, so this is technically the start of 4F1, 4F2, 4F3, 4F4, and that will be the last element in that block, right? So this is how you do electronic configurations. And we'll kind of do some practice with, I think, let's do zinc. Zinc will be, so the shortcut method is you basically you can do the similar thing, you just have to, the shortcut method involves, instead of writing it all out, you go back to the nearest noble gas. Remember, back to the nearest. So zinc, if you go back to the nearest noble gas, that's argon. So you just put argon in square brackets, and this is just a shortcut for writing 1s2, 2s2, 2p6, 3s2, 3p6. Instead of writing all of that, you can put square brackets argon. And then you have to add 4s2. So every time after a shortcut, you always follow with an s orbital, because your shortcut always includes a noble gas. It has to be. And then after the next electron after a noble gas will be an s electron, because that's the way the periodic table is arranged, right? So you start with the 4s2 after argon, and then zinc will have 3d10. Because you 3d1, 3d2, 3d3, 4, 5, 6, 7, 8, 9, 10 is the zinc, and so it'll have 3d10. If you look at gold, that's over here. So you have to go back to the nearest noble gas, would be xenon. After xenon, you have a 6s2 orbital. After 6s2, you go here down to the 4f14. So you're going to fill all those up. And then you come back to the 5d orbital, of which this is 9. So 5d9 will be the electronic configuration of gold. We said we are not doing these two because of the inherent confusion. I'll only give you ones from the D block, or the P block, excuse me, to make that less confusing. Okay, so that was that. We do have to discuss a new octet rule for these kinds of things, and atoms will like to have half-filled and fully filled orbitals. They do want to achieve basically noble gas configuration. They're going to try that, but a half-filled and full-filled orbital confers more stability on an atom than before. So, for example, the electronic configuration of copper and chromium. So yes, I did. So chromium here has argon 4s1 3d5 instead of what you might expect it to be. So chromium, if you look at it and start writing, you would have argon 4s2 3d4. That's what you would expect chromium to be. Argon 4s2 3d4. But because d5 is a half-filled subshell, it's more stable. So one of these electrons, even though it's D or 3Ds are slightly higher energy than 4s, will jump to a 3D because 3d5 gives it stability and therefore lowers its potential energy, which it wants to do. So chromium will have 4s1 3d5, and the same way copper will have, originally copper would be argon 4s2 3d9, but again, because a 3d10 orbital would be super stable for copper, you're going to have a 4s1 3d10 excitation of this electron to a 3d orbital. Again, nitrogen has 2p3, which is half filled, so it's less reactive than O. There's many other trends that you can talk about in terms of half filled and fully filled orbitals. The main ones we're going to do is just the copper chromium exceptions. That's going to be a question on your test, and that's about it. Here are some characteristics of S block and P block and D block and F block elements. Again, the P block I won't ask you because they're so variable, because there's metals, nonmetals, and metalloids. They form covalent and ionic compounds. They have noble gases. There's not really much in common with the P block, so it's not really a great question. You have to study each of the groups individually. S block, however, do have some general trends. They're usually soft metals, low melting points and boiling points, low ionization energies, low electronegativity, reactive, and form ionic bonds, except for beryllium because it has a 1s2 2s2, so that's kind of stable as it is, so it's not gonna do anything. But mostly you have to know any two of these things just so that you recognize the S block elements, right? Again, D block, transition metals. So we're going to talk a little bit about here metallic bonding. So we're going to get to bonding in the last part of the theory, but in terms of what you have to know, metallic bonding occurs when you have metal atoms, I should say metal ions. So let's take sodium for example. You have sodium when you just have sodium metal, right? It consists of sodium ions, and the electron is basically given up by the sodium atom, and it's kind of shared with the entire rest of the metal. So it's often thought of as ion islands in a sea of electrons, is a kind of way of thinking about it. And basically, because sodium loses that electron really quickly, all the sodium atoms lose their electrons, and the electrons kind of float around in between the sodium atoms. And this is what forms this electrostatic attraction, this glue basically between the positive and negative charges, what forms your metallic bond. So this is what keeps the metal together. It's the electron glue basically. So D block elements have an interesting, so the more glue that you have, the more tighter the bonding, the higher the melting point of the metal, because you require more energy to break those bonds if there's more stickiness there. And therefore, melting point increases with number of unpaired electrons. So the more unpaired electrons something has, the more electrons it donates to like roam around and form glue between the ions, and therefore the more tightly bonded these ions will be, the more unpaired electrons there are. So it has a higher melting point. So because manganese is stable with 3d5, it will not donate these 5 unpaired electrons, even though this has the maximum. It has 5 unpaired electrons, but these unpaired electrons are going to stick to the magnesium. The magnesium will not tend to become an ion and give these electrons out to float and share with other ions. It will hold these 5 electrons because it's very comfortable holding 5 electrons, because 5 electrons in a d orbital means it's stable. So vanadium has a 3d3, so this corresponds to the maximum number of unpaired orbitals in a d orbital, and so this will have the highest melting point of all. Zinc will have the lowest melting point because, again, a 3d10 structure confers extra stability. There's no unpaired electrons in zinc, and therefore no electrons are roaming around forming that glue. And so that zinc, mercury, and cadmium have the lowest melting points. Those are your 3d10, 4d10, 5d10 metals. You don't really have to know anything about the F block. They form complexes, they have variable oxidation states. I do have to say that they have multiple transition state, or multiple, now we're talking about oxidation numbers, they have multiple oxidation numbers because they can lose both their 4s and 3d electrons. For example, if we take iron, right? Iron has 4s2, 3d6, I believe. So it can lose 2 electrons, so it will probably lose once it loses 2 electrons, it will probably become a 4s1, 3d5, which is kind of stable, so it can form iron 2+. This 4s1 can also be lost to form just argon 3d5, in which case it becomes iron 3+, and so on. So you can have multiple transition states. Manganese has the most. It can form 2+, 3+, 5+, 7+. There's a bunch of different oxidation numbers for manganese, and that's just because the d electrons are not very reactive. So unlike sodium, so sodium has an s unpaired electron, right? It has a 1s1. Well, sodium has a 2s1. No, that's lithium. Sodium has a 3s1 electron, and though that unpaired electron is very reactive in the s block. In the p block, in the d block, however, for example, these 3 vanadium electrons or iron's electrons in the d block are not as reactive as a s block unpaired electron. Therefore, they will it's possible for them to exist in multiple oxidation states. They don't have to leave. So sodium will always exist in oxidation state of transition state of +1. Manganese and all the d block transition elements can have variable oxidation states. Again, in terms of why you need this, there's very few theory questions I can ask. Mostly if you do the review, you should be fine. This is just if you want to refresh your knowledge as to how to do these things. You can look at this video. I do realize I've run through them fairly quickly, but with some practice, you should just look at the practice videos, and hopefully that will better your understanding if you're still confused. Alright, signing out now.